So when you want to figure out a formula, all right, basically you take a sample of what you're looking for, the substance you found in your grandparents' garage, and you'd send it away to the chemist, and they would end up doing two types of tests on it. And the simplest one is just to find percent by weight. And that's not a very hard process to do with modern technology, but back you'd get information which looks something like what we're going to do in this problem. This problem, we've got a compound. It has boron and hydrogen, and it's 81.10% boron. Now, we saved a little money, and we didn't have them do a percent hydrogen test. But if there's only two elements, 100% minus the percent boron will equal percent hydrogen, so we can find it out. Weight percentages, which is what we're doing here, are going to lead to empirical formulas, the smallest whole number ratio. And remember, back at the beginning of this lecture, we talked about how empirical formulas are the smallest whole number ratios, but they may not be the actual molecular formula. So these mass percentages are going to lead us to empirical formulas, but they're not going to lead us all the way home yet. We'll talk about this. So to backtrack and make this simple, let's turn a mass percentage, like in this problem, into an empirical formula. What I try to do in problems like this is I assume 100 grams of sample. And if you assume 100 grams, then that means in an 81.10% boron, you would have 81.10 grams of boron. And in the chemistry world, we do everything by moles. So you've got to turn your grams of the elements into moles. So boron is 10.81 grams per mole. That would be 7.502 moles of boron in 81.10 grams of boron. Because I assumed 100 grams, 100 minus 81.10 will be the grams of hydrogen. And in your calculator, that comes out to be 18.90 grams. What this also means, of course, is that our sample was 18.90% hydrogen, but we were too cheap, apparently, to do that. Anyway, that's how you find the grams of the other piece. 100% minus the one you know gives you the one you don't know. Anyway, let's turn that into moles as well. So 18.90 grams divided by 1.008 grams per mole, 18.75 moles of hydrogen. So this is the moles of boron in the sample. If we have 100 grams, this is the moles of hydrogen if you assume 100 grams. And you could assume 1 gram, you'd have 0.8110 grams of boron and 0.1890 grams of hydrogen. But 100 grams is just really easy, so that's why I use it. But if you'd rather do a different number, go for it. Now, these two mole ratios, these two mole amounts actually are important. We're going to make like ratios out of them. You could write this as, if you will, a formula B₁.502H18.75. But that's a really ugly formula. And none of the formulas I've shown you in this class, or none that I ever will be that ugly. So what you want to do is you want to find whole numbers. And the easiest way is just to divide both numbers by the smaller. So 7.502 is smaller than 18.75. And 7.502 divided by itself is 1. And that's what I'm doing right here, all right? We're taking the bigger number and dividing it by the smaller number. That automatically means that the smaller number is going to be 1. And in this case, you end up with a ratio which is almost 2.5. Now, in a formula, you have to have whole numbers, no fractions, all right? So 2.5 times 2 would be one way to do this. Like you could have 2.5 moles of hydrogen per boron, but you won't see in chemistry like a BH 2.5. That would be pretty ugly and unusual. So instead of 1 to 2.5, let's multiply both of those by 2. If you do that, you will get whole numbers. Empirical formula here, B₂H5. So let's review the steps. We turn percentages into grams by assuming 100 grams. We turn the grams of elements into moles, and that's kind of a rough structure. And that's what I kind of was doing right here in the corner, but it's too ugly, all right? So we're going to divide both of the numbers by the smaller number, 7.502. You might get like a 2.5 to 1 ratio, and that's better, but you want to get whole numbers. So if you don't have a whole number, figure out a way to get it to a whole number. 2.5 times 2 is 5. If you do it to the top, you got to do it to the bottom. B₂H5 empirical formula. That's the smallest whole number ratio of atoms in this formula. This is not, though, the molecular formula. Boron and hydrogen form a whole bunch of different kinds of compounds, and B₂H5 may or may not be the one we're looking for. B₂H6 down there, a picture of it, that's an example of one of the compounds that happens between boron and hydrogen. Notice, if you're tricky, that there's a weird arrow going from the hydrogen to the boron right there, and another kind of arrow going from the hydrogen to boron right there. Boron is a group 3A element, and I'm going to call all the 3As, as I said earlier, twisted metals. And this is the first example we've seen of where boron, and aluminum can do this, and gallium, etc., why that's the case. That arrow means something, and we'll talk about this later. I'm sorry, I'm going to tease you right now with it, and I'm sorry, but just realize there's a reason for the arrow, and it has to do with these twisted metals. But anyway, back to the regular scheduled thing. We want to turn our B₂H5 empirical formula into a molecular formula. And what that means is our molecular formula could be B₂H5, like we saw water was 1:1, but it could also be the empirical times 2, which would be B₄H10. If you take the empirical formula and multiply it by 3, 3 times 2 is 6, 5 times 3 is 15, you keep B6H15, could be times 4, B8H20, etc., etc. So at least we know now that there's going to be 2 borons for every 5 hydrogens in the formula, but what is the final formula? What is the molecular formula? Molecular formula is kind of the holy grail of this section. To figure out the molecular formula, the holy grail, we need the molar mass of the compound. So when we sent that sample of the stuff we found in your grandparents' garage to the chemist, they did not only a weight percent analysis, which told us it had boron and hydrogen, or boron and hydrogen, in the sample, but we also have to do a second test. The chemist would do a second test, which was the molar mass of the compound. And that doesn't say anything about what's in the compound, like does it have hydrogen or uranium or arsenic or whatever, but it does tell you that in a mole of the molecule, you have that many grams. So what we're going to do is we're going to find the molar mass of the empirical formula, which is something we can do right now, and compare it to the molar mass of the compound. And if we do that, we're going to get a whole number ratio. And that whole number ratio will multiply by the empirical formula to get the molecular formula. So let's back up here a little bit. The stuff we found in your grandparents' garage, we don't know what it is. We sent it to the chemists. The chemists are really going to do 2 types of tests on it. The first one gave us the percentages by weight or percentages by mass, and we turned that into B₂H5. But the second test is going to be so many grams per mole in the molecule itself. So if we compare that number from the second test to the molar mass of the empirical formula, B₂H5, that's going to give us a whole number that we can use to find the molecular formula. And if that's as clear as mud, I understand. Let's go through some examples. Let's say that we have a compound. It has an empirical formula of CH2. So we already did the percent analysis, and we found it was 1 carbon for every 2 hydrogens. But in our second test, we find that the molar mass of the compound, 28.1 grams per mole. Remember, mole minus 1 means per mole. We can use this information to find the molecular formula, and it's not as hard as it might seem. But what we want to do is we want to first find the empirical formula's molar mass. We're going to compare that to the molar mass of the compound. And that did come from an outside experiment. This is a whole separate experiment. Now, CH2 has one carbon, which is 12.01 grams, and it has two hydrogens, 1.01 grams. So the molar mass of CH2, the molar mass of the empirical formula, 14.03 grams per mole. We're going to compare the 14 number to the molar mass of the whole compound, which is this 28.1 number. And this will always give us a whole number. No fractions, no multiplying by any integrals or anything. It's always going to be a whole number. So if you take 28.1 and you divide it by 14.03, you can probably see that's almost exactly a 2-to-1 ratio. That 2 is important. We're going to multiply the empirical formula, CH2, by 2. That means the molecular formula here, C2H4. So what we did a whole separate experiment to find the molar mass of the compound, 28.1. We calculated the molar mass of the empirical formula. In this problem, it was CH2, so that was one carbon, two hydrogens, 14.0 grams per mole. Molar mass of the whole thing, 28, divided by molar mass of the empirical, about 2-to-1. That means 2 empirical formula units per molecular formula. We multiplied the EF by 2 to get C2H4, the MF molecular formula. So CH2, the empirical formula, times 2 molecular equals the molecular formula. The simplest carbohydrate is glyceraldehyde. Its empirical formula is CH2O. The molar mass of the whole thing, 90.08 grams per mole. So which one of these represents the molecular formula? Now the molecular formula will be some ratio of CH2O. So CH2O and A, it could be. If you take CH2 twice, it would be C2H4O2. That would be answer B. Times 3 would be C. It definitely will not be E, because CHO would be 1-to-1-to-1. You have 2 hydrogens per carbon per oxygen, so that's not going to be right. What you want to do in this problem is you want to find the empirical formula's molar mass. So you want to find the molar mass of CH2O by itself. You'll add up carbon plus 2 hydrogens plus oxygen. Carbon's about 12, hydrogen's about 1 times 2, and oxygen's about 16. That comes out to be about 30 grams per mole. You want to compare that number 30 to the molar mass of the whole thing, 90. And you can see that 90 over 30 is about 3. That means you want to take your empirical formula 3 times to get the molecular formula. So the answer here does come out to answer C, the empirical formula taken 3 times. Now, back to how we did this. Molar mass of the empirical formula, 1 carbon, 2 hydrogens, 1 oxygen, about 30 grams per mole. Molar mass of the whole thing, 90.08 divided by 30. 3 is the ratio, and these ratios will always be whole numbers. So empirical formula was CH2O. Multiply it by 3, the number you just got. C3H6O3 is the final answer. Going back to our boron hydrogen compound, the empirical formula was B₂H5, and we want to find the molecular formula. What we're going to need is the molar mass. So if we do the molar mass of the stuff from your grandparents' garage, which is a whole separate kind of experiment, it comes out to be 53.3 grams per mole. And we can use this and the empirical formula to find the molecular formula. So just like we did with the last couple examples, let's find the empirical formula's molar mass, find the molar mass of just B₂H5. So B₂H5, 2 times boron plus 5 times oxygen, 26.67 grams per mole. So the molar mass of B₂H5 is 26.67. We then use that number, we put it in the bottom, we put the molar mass of the whole thing, this number, 53.3 in the top. You're always going to get whole numbers. This is a whole number of 2. So what that number 2 means, you want to take your empirical formula and multiply it by 2. So B₄H10 is our molecular formula, and that's kind of a cool thing. This is kind of a holy grail for chemists to find that number right there, that formula. Pretty cool. So when we did this problem, this is an overview, we first converted the percent by mass element values into moles. And I like 100 grams, but you can use anything you want. We then turned the moles into an empirical formula. You take the bigger one on top and the smaller one on the bottom. You might have more than two elements. The smaller one always goes on the bottom. And the idea is you want to get to smallest whole number ratios. So when the ratio we did, it came out to be 2.5 to 1, and that's better, but we want whole numbers. We multiplied by 2 to get B₂H5. That found the empirical formula. The molecular formula, we needed the molar mass of the whole thing, 53.3 grams per mole. We calculated the empirical formula's molar mass. B₂H5 came out to be 26.67 grams per mole, 2 borons and 5 hydrogen. That ratio will always be a whole number, no fractions or anything like that. And this ratio is 2 to 1. So we took our empirical formula, multiplied it by that 2 to get the molecular formula, B₄H10. If you follow these steps, you will be good to go all the way through the end of Chem 223, no problem. There are other uses of these kind of processes, and this is another example I'd like to show you. This is a reaction where you're taking some tin and iodine. The picture on the far left shows tin on the left and iodine, kind of a crystal, on the right. And you can heat the iodine up and it can dissolve in a solvent, depends on what kind of substance you're doing. Anyway, and you're putting it through a piece of filter paper, and you end up with an orange tin iodine. That's what that stuff is right there. But the question is, what is the formula of the tin iodine? Now, tin is a variable charge metal. Iodine is always -1. So the question is then, from this kind of data, like, how can we find the formula of the tin iodide? Using some experiment, we started with 1.056 grams of tin. We put 1.947 grams of iodine in with the tin, and at the very end of the reaction, we had some tin left over, some 0.601 grams. We isolated it with the filter paper. So what we're going to do here is we're going to find the grams of tin used in the reaction. We'll turn it into moles. We're also going to turn the grams of iodine, and by the way, iodine is a diatomic, have no fear of ice clear brew, so we're going to turn grams of moles into moles of iodine, and we'll compare the moles of tin and the moles of iodide to find the empirical formula. 1.947 grams of the I2 were used. The tin, though, we didn't use all of the tin up. Some of it was left over at the end. So we started with 1.056 grams, and we had 0.601 grams of tin left. So 1.056 minus 0.601 means we used 0.455 grams. Now, we're going to use that 0.455 grams and turn that number into moles, because that's the amount of tin that reacted with the iodine. So let's find the moles of tin. We're going to use the 0.455 because that's how much was used up. Tin is about 118.7 grams per mole. Still got the 3 sig figs going through, so 3.83 times 10 to the minus 3 moles of tin were placed into the beaker and used to make that orange stuff. We're going to do the same thing with the iodine. Now, you've got to be careful, because in a compound, you want just individual iodines. You don't want the I2. But the diatomics, like we talked about, always come in pairs. So for the molar mass, you want to use 2 times iodine. So 2 times the number for iodine, which is about 126.904, comes out to be 253.81. And so figuring out this number then is moles of I2. But in a compound with tin and iodine, or magnesium and iodine, or anything, you want just individual I atoms. So what we're going to do is we're going to convert the I2 2 into just I. So we'll multiply it by 2. There's 1.534 times 10 to the minus 2 mole of iodine atoms used in this reaction. Don't use the I2, you want just the individual I's. We know the moles of tin, we know the moles of I. So again, bigger on the top, smaller on the bottom. The iodine is bigger, it goes on the top, the tin goes on the bottom. You can see that this ratio is almost exactly 4 to 1. 4 iodines per tin, and iodine as iodide is always a -1 charge. So the tin has to balance the 4 negative ones with a positive 4. This is a tin plus 4. So we would call that compound, that orange compound, tin 4 iodide. And this is one way that people can find then the ratios or the formulas for these variable charge metals. Again, the nonmetals coming through, kind of a cool way that people can use.